we'll do an awkward pause here because I always start this and it seems like there's a big delay in it. Okay, so I assume it's going now. All right, so here I'm going to go through the steps to build that zee-section finite element model that I showed in class on Tuesday. So the things that you'll have to do for this week's homework and some of the subsequent homework will be very, very similar. So this again assumes that you have no background in using Hypermesh, and it's actually not that bad for doing these types of things anyway. So when you first start Hypermesh, you're going to get something that kind of looks like this. It's going to ask you for a user profile. So the idea of the user profile is this allows you to pre-process for different finite element packages like ANSYS or LS-DYNA or Nastran or whatever. So in our case, the easiest one to start with is OptiStruct. That'll work for us. So click on the one that says OptiStruct. I know it's a little hard to see some of my fonts because they're small here and I don't know how to make them bigger. But that's what it is. So I picked OptiStruct and hit OK. And now the environment is set up for using OptiStruct, okay? All right. So I use a lot of these panels down here, and they change depending upon which radio button you use. They're kind of set up to do, here's for doing geometric type of construction and operations, then another group that does one-dimensional meshes, 2D meshes, 3D meshes, other ones for setting up the analysis, load steps, and all that sort of stuff. And then other tools like delete things, move things from one collector to another, so on and so forth, okay? A lot of that stuff is also up here. I've been using this so long, I'm used to this old school interface that they originally had, but then they've changed a lot of them to also support regular pull-down windows. Over here on the left is a pretty important window. Make sure you have it, there's like 3 tabs up here, utility, mask, and model. It should be highlighted to model, so if that's the case, in here is where I get most of the finite elements, but like object creation things like for materials and properties and whatnot that I need to do here. Okay, I think we're ready to go. So the first thing we're going to do is I'm going to define a material. I'm going to define aluminum. Then I'm going to define a shell property card. That's going to define the thickness of the shells and what material that we use for the zee-section. Then I'm going to make the mesh, make the geometry, make the mesh, and then set up the solution load cases, okay? All right. So first thing I'm going to do, like I said, I'm going to create a material. So if you right-click on the little white area here, you'll get create, and you can pick a lot of things. So I'm going to pick material. And now I get a material here. I can give it a name. I'm going to call it aluminum. All right. And then down here are the parameters that go into that material definition. This is a Nastran Mat1 card. So you can see here it has the keyword Mat1. OptiStruct and Nastran pretty much use the same cards. So it's a Mat1 card. As we talked about in class, we just need to define 2 elastic parameters for an isotropic material. So I'm going to do Young's modulus and Poisson's ratio. So Young's modulus for aluminum, right, is 10 to the 6th. And then Poisson's ratio is about 0.32. You can put in the density if you want as well, but make sure you divide by 386 G, right, if you're using inches and pounds and that sort of stuff. But I'll leave that blank for now. Okay, so now I've got a material here called aluminum. Now I'm going to create a property. This is going to be a property to define the shell elements. So again, there are lots of different properties. If you have beam elements, bar elements, rod elements, springs, solid elements, they have different parameters that you have to set to them. We're going to set it to be a P shell. That's like the default, but you can see you can change it here. Oh, I'm sorry, change it here, card image. You can change it to different ones, but we are going to use the default P shell. And we can give it a name again, so we can call it aluminum plate. Okay. The material, we're going to pick the aluminum. So And now we have to at least define the thickness. And so we said, I think this is 90 thou thick. Let me just double check. That's what I said I did. Yeah, 90 thou thick. So 0.09 is the thickness. And that's it. So now we have aluminum plate. Now I'm going to start creating the geometry. The geometry and the elements are all going to go on a collector. It's kind of like a level, if you want to think of that in that sort of vernacular. So I'm going to go create component, right? And so we're going to call this, the component is going to be the zee-section. And under here, you can actually select what property is assigned to elements on that component. That's sometimes really useful. Sometimes it's not, because you have different types of elements and you can assign properties in different ways. But for us, all our shell elements are going to have the same property. So I'm just going to go here and select the property we just collected, the aluminum plate. So now every element in that collector, that component I should say, will use that aluminum plate property. All right, we're ready to go. We could probably save this as something. I'm going to save this as, where can we put this? Well, I'll just put it on the desktop for now. I'll call it example. So this saves the input, the preprocessor file, the Hypermesh file. All right, so now the next thing I'm going to do is I am going to start to create the geometry. So I'm going to draw the lines of that zee-section profile to start with. Then I'm going to mesh that with one-dimensional elements like lines. And then I'm going to extrude that mesh and get a shell mesh, okay? So I'm going to define first, we're going to go click geometry here. So I'm going to do geometric construction operations, right? So I'm going to go to geometry. And then we're going to create some nodes, which these are really like points. So I'm going to construct those at the corners of the zee-section. So there's a couple different ways of inputting nodes. I'm going to click the XYZ option way over there on the left, and I'm just going to type in the coordinates. So the we'll put the vertical line right at 0, and then the 2 points to the lower right and lower left. So the first point, if we do the upper left point, it's going to be at -3, 3, 0. And then we get this little tennis ball looking thing here. Now I'm going to put one at 0, 3, 0. Then I'm going to go down to 0, -3, 0. And now that it's a tennis ball that's down here, I'm going to scroll a little bit. I'll talk about scrolling in a second, if I can. Because I always use a 3D mouse. But there it is. Okay, sorry. And then the last point is going to be at 3, -3, 0. All right, so here we've got the corner points on the bends of the zee-section, right? So when you scroll, you know, you can use it like mostly, I think it's control with the different mouse buttons. So control with the left mouse button does like rotation. Control with the, that's kind of a cool one. Let me zoom out. If you do control with the middle button, you get this like little window and you can zoom in on it, okay? There's fit over there. And then the right mouse button is to pan. I think if you just do the middle mouse button, I guess it doesn't do anything, but that's it, right? Okay. So it's control, and that gives you those options, all right? All right. So fine. So now I got the points. I'm going to draw lines to connect them up, although I don't even think I need to do that. I think I can actually create a mesh of line elements between the nodes, all right? Let's see. So we're going to go to the 1D menu because now again we're going to make one-dimensional elements. We're going to end up deleting these, but these are just to help extrude to make the two-dimensional mesh. So here you can see there's lots of different types of one-dimensional elements one can construct. Masses, joints, bars, rods, rigids. They kind of fall along the nomenclature for Nastran elements. We'll talk about those, I guess. Not now. And so we're going to do a line mesh, I believe. And let's see, can I change this from lines to, yes, I can. So here the default is to pick lines. I haven't created lines, But if I click on this little left thing here, I can also make it go from nodes, and that's what I'm going to do. What type of elements do you want to use? Here you can change to be the whatever type you want. I won't get into it so much for this for now, but there's this name, but then you can assign an actual, like when you do plot elements, you can say, okay, make Nastran C-weld elements. When you do bar elements, make sure you use C-bar elements, or sometimes C-weld elements. So you can do that mapping. But let's not talk about that here because we really don't have to do that. So I'm just going to do plot elements. I think that's good enough. And I'm going to pick these two nodes. And the element size, about a ½ inch is probably okay. Let's do a 1/4 inch. We'll go with a pretty fine mesh here. So there's 12 elements along that line. If you click on that number 12, left click, it'll get bigger. If you right click, it'll get smaller. And that's one way to adjust. You can also adjust the bias so you can shift more elements to the right end or left end. Like you could do this bias. Like let's do a linear bias. So you can see here, it's sort of shifting the bias to the left end. If I right click, it goes back to where it was before. So I'm going to set it back to 0 so there is no bias. There are other types of biases you can do. Linear, bell-shaped, all that sort of stuff. But I'm not going to do that. Okay, so I'm good with that. That looks good to me. I'm going to hit return. And now I should have a bunch of nodes, elements there. I think I do. Let's see. I think we do. Okay, so now let's do it on the downside. Let's do it between these 2 points. So again, we're going to do a line mesh from this node to this node. Again, the same spacing, so that looks good. And then we'll go from here to here. Let's see if I can do. Okay, so I got to hit return. So that's good. They're there. And then we're going to go from that node to that node and mesh. And so fine. So now I've got a bunch of line elements there. Okay, so 12 here, and then like 24 there, and then 12 on the other one. All right, so now what we're going to do is then take these line elements and extrude them in the Z direction, right? Now, before I do that, I'm going to delete those big tennis ball nodes. These are temporary nodes. So go back and click on geometry. And then you can see there's this temp node thing. So I'm going to go temp nodes. And on the right, I'm going to say clear all. Excuse me. So that's going to get rid of all of those temporary nodes. I don't need them anymore, and sometimes you can select them and they kind of cause some issues because you're not selecting the actual element node there, but you're selecting that temporary node. So this is easier. All right, you can save again. And now we're going to do the extrude. So to do the extrude is going to be under 2D because we're going to extrude 1D elements to make 2D elements. And they don't really call, I guess they call it drag. So right here, there's a drag. Before I do that, there's different ones in here. Some of the ones like auto mesh is really useful. If you have some sort of surface, it'll automatically mesh those surfaces. Planes are nice. If you have like a 2D region in a plane, it'll mesh that quite well. You can do ruled ones for ruled surfaces and whatnot. So, but we're going to do a drag, right? We're going to do this extrude process. So I'm going to pick drag, and it wants me to drag elements. So I'm going to drag all these elements. So you can see there they are. I'm collecting them. I can also go here and click on the way to select it. And I'll just say all that are displayed. And now you can see all those are displayed. Another way you could do that, I'm going to unselect them, is I'm going to do it by window. And you can kind of pick window points, like lassoing it, and then pick all those elements. You can do it that way. Then or you could use on a plane, adjacent. There's lots of useful ways here for selecting things that are really specific to find an element type of data. But anyway, so let's just do display, and there we go. Okay, now we're going to drag along the z-axis. So I'm going to set this to z-axis, and the distance will be 48 inches, and it wants you to pick the number on the drag. Okay, so if we use 96 there, that means the elements will have a length of about a ½ inch. So they're a little bit longer in the bending direction, but only a 2-to-1 aspect ratio, so that's not too bad. So we're going to do that, and then we're going to hit drag plus. And that's going to extrude in the positive direction, the positive z-axis. You can do drag minus, and that'll extrude in the other direction. But we're going to do drag plus. And now you got it. Now you can see you have a bunch of extruded shell elements. Okay? I'm going to return that. I always have a tough time getting this to, and I like to see these shaded instead of like wireframe. So if you pick this little shaded little block down here, it'll shade them, and I think that looks nice. If you want to change the color, like that yellow color is kind of annoying, you can go over here into the component selection, and if you change this, I can make a nice blue color, so be it, right? And so there you go. There is my shell mesh. It was that easy, okay? So now we've got all the shell elements. I'm going to delete those line elements, right? So how can we do that? Well, we're going to go under Tools and then Delete. Now the thing we want to delete are elements, so I'm going to go here and pick elements. Well, you can see if I click this one. There's all other things you can delete, but we're going to do elements. And I can just try to click on them. And oh yeah, I'm selecting them. There they are. That's one way to do it. I think another way to do it is I could select on plane. Let's see if I put by on plane. And I can pick 3 points on the plane. Let's see if that selects them. Oh, see, that selected all those. That's nice. So that's another nice feature to help select. And now I can delete those. I'll save it. All right, so now we just have the 2D shell elements. Now, we can't run it yet. We have to define the fixed boundary conditions as well as the load boundaries conditions, and then set up a load step, the fact that we're going to do a linear elastic solve. So let's first do the fixed boundary conditions. All the boundary conditions are typically assigned through this radial block here called analysis. So let's click on that. And then you can see different types of boundary conditions, for lack of a better word, that you can assign there. So the first one we're going to do are going to be constraints. We're going to fully fix this left end. So I'm going to pick constraints. And now it wants me to select the nodes. And then I'm going to fix all these degrees of freedom, all 6 degrees of freedom at each node to 0. So it's going to be fully fixed there. So again, to pick the nodes, we can use the plane option. And I can just pick 3 nodes on the plane, and it should select all those. So that's cool. Another nice feature is this by path. Let me show you that as well. So you can also do by path. Where's that? By path. And what that allows you to do is, like, you pick one node, and then what it'll do is it'll select all the nodes between your clicked points, like on that path. So if I get this one right, see I got all those. So that's another really useful one. So we're going to create that. We created new ones. You can see actually it added a load collector here. So this auto 1 is what's holding those boundary conditions. So I'm going to change that to, let's rename it. We'll call it bending. Because this is going to be the bending load case, the boundary conditions for bending. It's the only one we're going to use. All right, fine. So now we have the fixed boundary conditions. Now the next thing we need to do is put the force on the right-hand side. So to apply the point force on the right-hand side, I am going to use what's called an RBE3 element. So it's going to be like an element that allows you to span forces, loads over several elements. So the idea is we want to basically kinematically span that 600-pound downforce over all the nodes on the edges. So that element does that. So we're going to create one of those. So what it looks like is it's like one dependent node driven by a whole set of independent nodes. So the independent nodes are going to be the nodes on this plane, and then I need the dependent node, which I'm going to put right here at the middle, and I believe I have I'm going to put it right here in the middle, and I'm going to push it out a little bit so I can easily select it, I think, right? So again, first we're going to create a temporary node to do that. So I'm going to go back to geometry, create node, and here I'm going to use the option that allows me, this one here, that allows me to select, create nodes in between two nodes. You can pick one node in the middle, 4 equally spaced nodes, however you want to do it. So I'm going to pick this point and this point, and I'm going to put one node between. So I hit create, and there it is. So that is my node. Now, it's right on top of the other node there, so it'll be a little tricky to select. So I'm going to just move it out a little bit in Z so I can easily select it and then move it back. I don't know, it's the easiest way for me to do it. So to move things, like I'm going to go to analysis and then pick translate, which is, oh, I'm sorry, it's not analysis, tools. So you go to tools and then there's translate. And we want to translate a node, so I'm going to click on the node. And I'm just going to move it out 1 inch in the Z direction. So I got 1 inch here, we're moving in the Z direction, so I'm going to do translate plus. And so there it is. All right, so now I'm in a position to make my RBE3 element. That's a one-dimensional element. It's under that bin, so I'm going to click on 1D element, and here you'll see actually one of those bars called RBE3, so I'm going to click on that, and we're going to have all 6 degrees of freedom as dependent, so leave that the way it is. We're going to select the dependent node, that's this tennis ball, and then the independent nodes, that's going to be the ones on the plane, so we can pick plane, I guess. And we'll pick the 3 points with 83 points. So that looks good. So let's create it, and so there you go. So now you can see I get this like spider webby looking thing. All right, let's get rid of the temporary nodes. So I'll go back to geometry, temp nodes, clear all. So now that one's gone away, and now I've got this spider web here, right? So this is where I want to put the force, right at that node. Okay, so I'm going to apply the 600-pound down force in that node, and what that's going to do is apply that kinematically over this entire edge, the independent nodes from the RBE3 element. So analysis, and we're going to put a force. So here's forces. It's going to put those into the bending collector. So let me select the node that I'm going to put the force. There it is. It's in the Y direction, and it's going to be minus 600 pounds. So everything here is fine. You know, there's different ways of selecting the magnitude of the force. We're going to just type in the magnitude, and the direction is defined by an axis. So now I'm going to create, and there you go. Change the color of this so it looks a little better. All right, so there you go. So now we've got the force here and then the fixed left end. So I really shouldn't have the force out an inch more than it needs to be. That's going to add extra bending moment onto it, which really isn't physically there. So I need to move that little point back 1 inch. I just moved it out so it was easy to select. I probably could have selected it without moving it out, but I don't know. Sometimes it doesn't work that way. So again, we're going to go under Tools and then Translate. We're going to pick that node. It still had the same options as before, so it's a Z-axis, magnitude of 1. So instead of translating positive, I'm just going to translate negative and move it right back. And now that point is back on the mesh. So the node that the force is applied on is that node of the RBE3 element. It's not the node that's on the shell element mesh. Even though they're right at the same point, they're not connected. So the force is on the RBE3 dependent node, which then kinematically distributes the force to all those independent nodes on the RB3 melt, the edge of that zee-section. So even though it's right there, it's not like it's applying it to this node on these two shell elements. Okay, so it'll kind of distribute that. So that's what we want. So that's all good. So actually, we have the mesh, the material properties, the shell element properties, and the boundary conditions. Before we solve it, the last thing we need to do is we need to define the load step. So again, we're going to go into this left window here and right click, and under create, we're going to select the load step option. And so there it is. There it is. And now it's going to give us the fields for defining a load step. Let's give it a name. I'm going to call it bending load step, whatever. All right. So this is going to be a linear static analysis. So under analysis type, let's click on that and not use generic, but let's go way up to the top and click linear static because that's the type of analysis we're going to do. And all we really need to do here is define the load collector that has the SPC constraints, the fixation constraints, and the load collector that has the forces. They're both in the same load collector, so but that's fine. They can be in separate. So if you wanted to do multiple different load cases, like different forces, you could put each one of those forces for the different load cases in a different load collector, and then have multiple load steps that run that simulation, okay? But we're just gonna have one load step with the SPCs and the forces from that one bending load collector. So to define that, we go under SPCs, and if we click on the unspecified, you see it wants you to pick a load collector. So I'm gonna pick the yellow thing, and then I'm gonna just pick the bending load collector. And you can see there's the SPCs. I'm gonna do the same thing to say, okay, use the forces on that load collector as well. So I did the same thing there. And now you can see we have bending. If you want to write out different options here, you can select those. Like you can pick different things to output, maybe somewhere in here. Where is it? I think output is should under here. Output, right? So you can click on this little button and you can spend out all these options to write out reaction forces, so on. We really don't need to do that for this analysis, so we'll just leave that as it is. And there we go. I think we're ready to run it now. So everything's there. We have the material and the shell properties defined. We have the finite element mesh. We've applied the constraint and load boundaries. And we've defined a load step that uses those in a linear static analysis. So now all we have to do is solve. So actually, this is one of the nice things about using OptiStruct in Hypermesh is you can execute the solver right from this interface. So if we go under analysis, you'll see this button down here says OptiStruct. So you click on that, and that'll allow you to solve. So here's different parameters for solving. Most of these, the standard ones, are good. Like run option is usually either doing optimization or analysis. We're going to do an analysis. If you do it as optimization, it'll still work anyway, but analysis just does the analysis. And yeah, everything else is good here. You can select the memory and all that stuff. And we're ready to do it. So I'm going to click on this green OptiStruct button, and that's going to start solving it. So we'll get another little pop-up window that shows it's starting the solution process. It'll give some information. If you get an error, say you forgot to assign the shell properties, or there's no material assigned, or you didn't set up a load step or something like that, you'll get those errors in the message log. But this one successfully solved it, so it's ready to go. And so I'm actually going to stop the video here. The next thing I'm going to do is show you how you look at your results in Hyperview, which happens when we click on this result button. But I'm going to stop the video here for now, okay?